In the previous part, I introduced the definitions of three-dimensional stream function vector and potential function, and the main assumptions behind them, and the validity of the Laplace equation to compute the magnitude of these functions. Okay, let's discuss some extra remarks about these two important functions. Both of them, this is the stream function part, and the right side in the board is the potential function. Both of them are scalar quantities. As I told you, the stream function originally is a vector quantity, but we can simplify it for two-dimensional flows to obtain a scalar stream function. So the stream function is a scalar quantity similar to the potential function, but the potential function originally is a scalar quantity. Both of them are kinematic properties, and the dimension of both of them are identical, L2 over T, and the unit of both quantities in SI system of units is a square meter per second. The definitions, the velocity vector is defined as the curl of the potential stream function vector when the flow is incompressible. In two-dimensional space, U is the partial derivative of the scalar stream function with respect to y, and V, the vertical velocity component, is the negative of the partial derivative of the scalar stream function with respect to x. Similarly, if the flow is irrotational, here the flow is incompressible. In the potential function context, the flow must be irrotational. The velocity field can be written as the gradient of the scalar field, which is the potential function. And in three-dimensional case, the velocity components are equal to the partial derivatives of the phi function. Here, if the flow is irrotational, in addition to the incompressibility, the flow is irrotational, the governing equation to compute the scalar or the vector stream function is the Laplace equation. So this equation holds if the flow is irrotational and incompressible. Here, if the flow is incompressible, again the equation which governs the potential function is the Laplace equation. So the assumption behind this equation is the incompressibility and the irrotationality of the flow field. We can write the extended form of this equation for compressible flows, which yields a very huge and long equation and is nonlinear. You know, the Laplace equation is a linear partial differential equation, but the compressible form of the Laplace equation, which is used when the flow is not incompressible in compressible flows or in gas dynamics, we obtain the compressible form of this equation, which is nonlinear, which is a nonlinear huge equation. And again, when the flow is rotational, the Laplace equation fails to predict the flow field. For example, in Blasius flow over a flat plate, the flow is incompressible and two-dimensional, and this definition is valid. But you cannot use the Laplace equation to compute the psi function there. So in flow over flat plate, in boundary layer theory, we find another equation for psi for rotational flow over flat plates. Another point is that the definition of the stream function comes from a physical governing equation, which is the conservation of mass or the continuity equation. As you see, the divergence of the velocity field equal to 0 is the conservation of mass, which is a physical aspect. But the definition of the potential function comes from mathematical theory. So this is a pure mathematical definition, but this is related to physical understanding of our physical understanding.